All right, let's talk about periodic trends. Okay, there's going to be 4 trends that you need to know. All right, and these are just trends that the periodic table follows just as you're moving left to right or top to bottom, anything like that. So the first one that we're going to talk about is atomic radius. All right, and then a solid definition for atomic radius is the distance of an atom to the valence electrons. Okay, and the trend, if you're looking at a periodic table, the trend for this is that it decreases going left to right, okay, and it increases going top to bottom. Okay, so it decreases going left to right, it gets smaller going left to right, and then it increases going top to bottom. Okay, so if we were to look at a picture of this, okay, this right here, you can see where as you go down, okay, as you go down, it's gaining energy levels. And in one of the previous videos, we talked about how each period has more energy levels. So this one has 1 energy level, 2, 3, 4, 5, and 6. So as you're gaining energy levels, we draw quick Bohr models. You can see that as you go down, you gain energy levels, you gain overall radius. Okay, they get bigger. Okay, now as you go across left to right, it gets smaller. Okay, going left to right, you're getting smaller. So lithium is larger than beryllium, is larger than boron, carbon, nitrogen, and so on. Okay, and it even has the radius number there for you. Okay, and the reason for that is what's called effective nuclear charge. Okay, so effective nuclear charge is basically the charge in the nucleus. So as the effective nuclear charge gets greater, moving left to right, it just means that there's more protons in the nucleus going left to right. Okay, and because everything on this energy level only has 2 energy levels, you're not gaining any energy levels. You're not getting anything that's further away from the nucleus. So if you were to think of it as like a bunch of kids standing on a trampoline, okay, if this is our trampoline, you've got kids here and here and here, just standing on the edges. Okay, as you add more kids to this middle, it sinks down further and further. Okay, and then as it sinks down further and further, it's harder for these kids to stay on the edge, so they start sinking down a little bit too. Okay, and the radius of the kids gets a little bit smaller the more people you put right there in the middle. Okay, so effective nuclear charge is gonna basically cause this trend in atomic radius. Okay. Let's move on down to the next one, which is ionic radius. The ionic radius, much like atomic radius, is basically the radius of an ion instead of a neutral atom. Okay, so when an atom loses an electron, it gets smaller. Let's talk about why that is. So if you have, let's say you have lithium here, okay, lithium, and you're 1 electron, okay, it's going to lose that electron, okay, obviously we've gone down a whole energy level. So now it just looks like that right there. Okay, so that's pretty obvious. But let's look at one that doesn't go down an energy level. Let's look at beryllium. Okay, so we've got beryllium here, and it's got 2 electrons. Well, if it loses 1, now 1 valence electron, and it still has 4 protons. So it has 4 protons pulling on only 3 electrons. So the effective nuclear charge, like we just talked about, is now greater when compared to the number of electrons. Okay, so it can pull those in just a little bit tighter. Okay, when it's got when it has more when it has more protons than it does electrons. Okay, when an atom contains electrons, it's bigger. Okay, and for the same kind of reason. So let's say we're looking at one that, let's say we're looking at oxygen. Okay, it has 6 valence electrons. Okay, if it adds more, okay, 1 or 2 more, it's going to get bigger. Okay, and the reason is, let's draw on this real quick. The reason is it now has, if we're looking at oxygen, it now has 9 electrons and only 8 protons. So those 8 protons can't pull on those 9 electrons like they were able to pull on the 8. So as we add electrons, that nucleus can't pull on those electrons as much, so they kind of separate a little bit. Okay, it's like if you've got a bunch of kids standing in a circle holding hands, okay, and they spread out as much as they can, they're going to form a nice big circle. Okay, but when you add some, let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 there. So if we add 1, it's got to be a little bit bigger. Okay, it doesn't really look like it, but if you stood there with your hands held and you step back, okay, the circle would be bigger here than it is right there. Okay, so every time you add an electron, you just get a little bit bigger. So let's look at a picture of this. Okay, we don't need first ionization energy. Let's look at a picture right here. Okay, this is your ion size. So again, it gets bigger as you go down, okay, and it decreases as you go left to right. Now, the one kind of caveat to that is right here. Right, it resets when you get to negatives. Okay, so it resets here, but then follows the same patterns. It still gets smaller as you go left to right. Okay, and still increases as you go top to bottom. Okay, so once you get to nitrogen, okay, nitrogen, this group 5 here, group 5A, once you get to that one, it blows back up and then continues on with the same trends. Okay, so let's look at, kind of getting my pictures a little messed up here. Okay, let's look at ionization energy. Actually, before we go to ionization energy, let's talk about Isoelectronic Series. Okay, that is just a series of ions or elements that have the same number of electrons. Okay, so if you were to look at a periodic table and you picked out, you know, if you picked out neon, okay, if we go back up to a periodic table and just look at it, okay, you picked out neon, all right, it has 10 electrons. So you need to find a couple more things that have 10 electrons. Well, fluorine has 9 when it's neutral, but when it has a charge, it has 10 electrons. F minus has 10 electrons. Okay, so you can go left again and go, okay, well, oxygen in its neutral state has 8, but if we add 2 electrons and make it a negative, it also has 10 electrons. You can also go the other way with it. Okay, sodium. Sodium has 11, but if you take the 1 away and make it a positive charge, it now has 10 electrons. Okay, magnesium. Magnesium has 12 electrons, but when you make it into its ion, take 2 of them away, now it has 10 electrons. So all of these have 10 electrons. The easiest thing to do is to find one noble gas and then go 2 to the right and 2 to the left. Okay, find 2 positives and 2 negatives that are right next to each other. Okay, that is an isoelectronic series. So let's move on down to ionization energy. Out of the way. Okay. So ionization energy energy required to move an electron. There's first ionization energy. You'll see first ionization energy right there, and there's second and third and so on. We're only concerned with the first one. Okay. And this, as you can see from our picture down here, it decreases, or sorry, increases. Yep, it increases left to right. Okay, and then it also decreases going down. So if you'll look, helium has the highest ionization energy. All right, so let's talk about why that is. Why does the trend move left to right? Okay, and it's all about getting rid of an electron. Well, let's look at sodium or lithium. Okay, each have 1 valence electron. And like we talked about in one of the previous videos, it wants to get 8. So is it going to be easier to get rid of 1 or take on 7? So because it's going to be easier to get rid of 1, it's going to be very easy to just, if this is lithium, okay, it's going to be very easy to just get rid of that 1. It's not going to take a whole lot of convincing, okay? As you move across, we go all the way to fluorine, okay? Fluorine has 7 valence electrons. And again, it wants 8. So what's going to be the easiest thing to do? Is it going to be easier to get rid of 7, or is it going to be easier to take on 1? Well, it's going to be much, much easier to take on 1. Okay, so it's going to be very, very difficult to remove any. So if you wanted to remove 1, it needs 1. So if you want to take it away, it's going to take a lot of energy. Okay? And then by the same token, if you have something like helium or neon, we'll do neon, okay, that has a full valence shell, it doesn't even want to react with things, let alone give up an electron. Okay, it already has an 8 electron valence shell, which is what it wants to be stable. So now this is very, very stable. Okay, so it's going to take a high amount of energy to remove 1. So very high energy to remove. Okay, so that's ionization energy. How much energy is it going to take to get 1 of your electrons? Okay, like how much money is it going to take to buy something from somebody? Well, if they value it, like neon or the noble gases, or even these halogens, like they value their existing valence electrons, it's going to take a lot of energy and a lot of money to get whatever they want. Whereas something like lithium, its valence electron, it only has one, it doesn't really want it anyway. It's not going to be hard to take that away. Okay, let's move on down. The last one. Last one is electronegativity. Okay, so electronegativity. Okay, basically, does an atom take on additional electrons? Okay, so this is kind of similar to ionization energy. Okay, and the trend. So the trend again increases going left to right and decreases going down. The only difference is right here. These noble gases. Noble gases show electronegativity. And why is that? Why do they not want to gain any more electrons? Because they already have 8. They already have a full valence shell, so they don't want to gain any. Okay, so it's going to be very difficult for them to do it. They have none. Okay, fluorine, you'll notice fluorine has the highest on the entire periodic table. Cesium down here, if we're not counting the noble gases, cesium has the lowest. Okay, so it kind of follows a general trend of that right there. Okay. So your trend is increasing going left to right and decreasing going down. Okay, and remember that the noble gases have no electronegativity. Okay, so if I were to say, put these in order of smallest to greatest, and I said, okay, we've got iron, we've got fluorine, and we've got neon and cesium. Okay, if we go smallest to greatest, the smallest one, okay, technically is neon because it doesn't have any, because it falls into that noble gas category. So we would put that one first, okay, and then what's left over is cesium. We already talked about cesium having the smallest one of all the ones with actual values attached to it, okay, and then iron's right there in the middle, and then fluorine has the highest, so fluorine's last, okay, so this is increasing, right? So those are the 4 periodic trends that you need to know and their directions.